Okay, this is a video about the combined gas law. And with the combined gas law, we're working with the three gas laws that we've already learned, Boyle's, Charles, and Gay-Lussac's law. And we're actually just going to combine those into one big equation. And the difference between any of those and this combined gas law is that we've got temperature, pressure, and volume values that are all changing. And so where we left out, so if you remember, these were the equations for Boyle's, Charles, and Gay-Lussac's law, and you can see that they only involve the use of two of the three variables, but the combined gas law has them all in motion. So the equation for this is as stated: P1 V1 T2 equals P2 V2 T1. And the reason we call it the combined gas law is it's really just a combination of the gas laws that you already have learned. So if you just look at the P's and the V's, you see Boyle's law. If you only look at the P's and the T's, that's Gay-Lussac's law. Or if you only look at the V's and the T's, that's Charles' law. So all we're doing is just combining them all together to make one big equation. And here we have 6 variables, and what we do is solve for 1 out of the 6, which means that you have been given the other 5 in a question, or you at least have the ability to get 5 of these 6 variables before you solve for your unknown. So let's do a practice problem here. 250 liters of gas at a pressure of 1.4 atmospheres, a temperature of 42 Celsius, is heated up to 97 degrees Celsius, and its volume doubles. What pressure does that gas now exert? So here we're gonna line up our equation here, but the first thing we want to do is look at our temperatures, because 42 degrees Celsius, we're gonna have to add 273 to that. Oops, 42 plus 273, that gives us 315. Okay, now when we have a second temperature here that we've also got to convert. 97 plus 273 is 370. Okay, so these are your Kelvin temperatures that you're going to use for your T2 and T1. Okay, so let's just plug everything in here. So our initial pressure is 1.4 atmospheres times our initial volume, which was 25 liters, times our final temperature. That's where you can go wrong. You could get on a roll with your initial values and put the wrong temperature in accidentally. I do that all the time. But it's starting at 42, or it's starting at 315, and it's ending at 370. Okay. Set that equal to the other part here, which is our final pressure. So our final pressure, that's what we're solving for. What pressure does that gas occupy now, or exert now? So our P2 is what we're solving for. V2, the volume is doubled, right? So the 25 liters that was our initial volume, it doubles to 50 liters. And we have an initial starting temperature of 315. Okay, now it's just basic algebra. We want to isolate that P2, so we would divide both sides by 50 liters times 315 Kelvin. We do that on both sides. Times 315 Kelvin. Okay, and that makes them cross away from on this side here, and that just leaves P2 by itself. And now it's just multiplying and dividing, right? So 1.4 times 25 times 370 gives us this number, which we're going to divide by the denominator, which is 50 times 315. And that gives us a excuse me, a final pressure of 0.82, and we're stuck with those two numbers here. So 0.82 0.82, and the pressure unit you're going to use just matches the pressure unit that you have in the problem. So 0.82 is calculated in atmospheres, and that's all you do. So it's not terribly challenging, I don't think. Just a little bit of algebra. All right.